Everyone, okay, so this is the quick video to do the assignment for ENG 766. So looking at this here, we're going to be looking at a simple beam, cantilever beam. It's 500 millimeters in length, 20 by 20, and has a force of 100 newtons on one end. So what we're going to do is look at this one in a sense that you are required to use ANSYS, FEA static structural, to look at the material properties for structural steel. And we're going to be doing some basic simple hand calculation, so determine the hand calculations for a simple beam. And then from there, what we're going to be doing is comparing the theoretical with the numerical in terms of the bending, deflection and stresses. After that, we're going to be using the space claim to conduct a design optimization to reduce the material by using the shell fill function in the space claim, and then comparing our validation model against the new models that we've created by reducing the material weight, and then obviously conduct a fatigue analysis on these as well. So basically, first of all, what you would need to do is work on your Excel sheet. If you've got Excel sheet, that's really good. You can use hand calculation. So by here, you can put your values in, and we know what the actual deflection is in meters and millimeters here, and we know what the maximum permissible stress is for this given problem. So in your assignment, which had to be written in as an IEEE paper conference paper, we would like to see all the equations written in the correct format, as well as the values calculated. So opening up ANSYS, what we want to do is do the benchmark model first. So static structural analysis, right click, design modeler. Give it a few seconds for it to load up. In here, make sure your units are in millimeters, XY plane look at, and then what we're going to do is create a primitive box, and the box length is 500 millimeters. In the Y direction it's 20, Z direction 20. We need to centralize this, so minus 10 in the Y, minus 10 in the Z, and you'll see that that's nice and centralized. Press generate. So now that we have our beam, it may be an ideal point to export this so we can regenerate it back into space claims. So export. I've created a folder called ENG766, and in there what we want to do is IGS, call it beam, save, and we go file, close, design modeler, double click on model, now, once the model takes a bit of a while to load up, we just make sure it's correct, so solid structural steel. One thing that it's very important to take into account is the properties, and it's the mass. So we know that this is 1.57 kilograms of mass, and this is something that we want to be able to record, because for every model you'll be doing, you'll be reducing the weight and comparing that against its performance in terms of deflection and stress. So remember, the mass is something that we need to be comparing with. In terms of mesh insert method, we select the body, apply, and what we're going to do is we're going to use tetrahedrons, and for a generic mesh at the moment we'll just use 2 millimeters. As you can see, the red circle there represents the dimension, the mesh size. So just press generate mesh. We're obviously just using the standard model there. So static structural wise, fixed support on this surface here, and then obviously a force load, not on the surface but on the edge here of direction wise, and in the assessment brief it tells you that it's a force of 100 newtons, so minus 100. Surface, press solve, give it a few seconds and it should solve it. And the solution, deformation, total, stress, we can give it the normal stress, press solve, and again, so we can see the deformation here and the normal stress here, 67.04, and total deformation is 1.5. So going back to the Excel sheet here, so we can see that the force is 150, change that to 100 newtons. So we can see that the deflection is supposed to be 1.56. We can see that that's 1.56 there, but the megapascals is 37.5. You can see the normal stress here is quite high. So what we want to do is, we know that it's very, very high due to being constrained here. So what we're going to do is add a construction path, and we'll do it on the top surface because then we can compare with all our models on the top surface here. So we want to go 10, 10, in the X direction here is 500. But what we're going to do is we're just going to skip a little bit on here. So we're going to go, say, 1.9 millimeters away from the model, from the actual fixture, and then again stress, normal stress, this time path. We could add our path here, press solve, and we can see here 37.53, and you can see 37.5. Yeah, so it's near enough a match. As we're here as well, because you can measure that normal stress, megapascals there, we can also do a deflection as well. So deformation, total, select path, and select our path here, and press solve. You'll have a really nice graph showing you the maximum deflection as well, which you can do for comparison. Now, as this is our benchmark model, we might as well put in our fatigue analysis. So in here, insert fatigue, fatigue analysis. So we've got that there. We know it's going to be a factor of 0.8. We've got stress life, 1 cycle, 1 misses, that's correct. And then we need to insert in a safety factor, and that's going to be 1e to the power of -6. So there. And also what we want to do is insert in a biaxial indicator, press solve. So here now we have our safety factor as well as our biaxial indicator, and insert in a fatigue sensitivity as well. So what we can then do is get a fatigue sensitivity graph, which you can export into Excel. So you can actually export this as a text file and then import that into Excel, so you can do a comparison study between your different models. So now that we have our benchmark model done for this solid model, you can take your nice pictures and everything for your assignment, but mainly it's the values in terms of weight, maximum stress, maximum deflection, safety factor, biaxial indicator, and the fatigue sensitivity, which we'll be comparing. Now, what we want to do is obviously here, delete. We want to be closing this, so file, close mechanical, and in our static structural here, We can either duplicate this later on and replace the geometry, but what we want to do is we want to bring in a component system, say for example geometry here, and this geometry, what we're going to do is we're going to import in a geometry browse, and we'll bring in the beam, open, right click, and edit this in Space Claim. Give this a few seconds. Now, what we're going to be doing is we're going to be filling in this body with a shell function. So, in order to do this, usually the Space Claim does fill in the shell, but for some reason it creates multiple part bodies. So, rather than subtracting them individually one by one, what we can do is we know that the overall shell thickness has to be a minimum of 2 millimeters. So what we can do is we can go to design, go to plane, either one of these surfaces, doesn't really matter which one you pick. So we just say, for example, pick this one here, and it creates a plane. Now what we can do is we can press escape, move, we select this plane, and we click on this axis and just move it down until the value comes in, and we put 2 millimeters. So what that happens is it just creates a plane 2 millimeters away from there. Actually, hold on, Control Z, Control Z, Control Z. We must select this Z face here to create the plane. Reason being is because every extrude we do for the shell fill will be in the Z axis. So select this, we create that plane. We want to now move this plane in the Z direction 2 millimeters. So that's, you can see that there, it's in 2 millimeters. And then what we're going to do is press escape, and what we're going to do is we're going to use the combine function. We select this body and we select this plane, and what you'll see is it's created another solid. And that's what we're going to do is to cap it up. So we deselect that plane. You can actually suppress physics so it doesn't get exported out. And what we do is we suppress this one, this new shell that we created temporarily. We then click on facets, shell, fill this in. We want the inside to be 2 millimeters. And here the basic. So here what we have is we've got some shapes. We've got 2-dimensional square infill pattern. We have 2-dimensional triangular infill pattern. We have 2-dimensional hexagonal infill pattern, and this is 3-dimensional. We'll try and ignore the 3-dimensional. We'll just focus on these 3 here, and we will have a variety of different shapes and fills to see the strengths in comparison. So here we can see you've got a fill percentage, a length, and a thickness. Now the length, you'll see by changing this will have an effect on the fill. So if I put this to 5, it will give you 59.6%. But then here you've also got the thickness of each of these. Now if the outside is 2 millimeters, keeping this one 2 millimeters keeps it nice and confined. So everything is 2 millimeters. So thickness is 2 mil. The inside or the outside shell thickness is also 2 mil, and you can now start playing around with the length. So, you know, having 2 millimeters will create something like this, 4% fill, and obviously we don't want to reduce more than 50%. So, you know, 6 gives you something like this. So let's go with 6. Then you can go with 7, and you can see that that starts, you know, making the size a bit more bigger, depending on what you want. So, just say for example, we went with 6. Now, you can do it by fill, but fill will automatically do everything for you. So, say for example, 20% does something like this, 50% gives you something like this, 60% gives you something like this. So, sorry, 60% gives you something like this. You know, so again, completely up to you. How you do this it's your parametric study. So you can either go with the fill percentage or the length percentage. So if we went with the 30%, so let's go with 30% here. So press generate and it will create this facet for you, as you can see. And now if you right click on that facet, convert and merge faces, it creates all of these solids. Oh, sorry, press Control Z again. Now what you want to do is, once you select your 30%, you need to select this surface body and say up to this surface. Press generate and then right click, convert to solid, merge faces, and it does something like this. Now remember, we had this additional surface here, shell body that we created. What we're going to do is we're going to go to design, and we're going to combine, reselect that one again, so that body plus sign with this one, and as you can see now it creates one shell body, and that body there again, if you display as wireframe, you'll see it has all its structure inside that you need. So again, so this is just one model. We can now go to File, Close, or Exit Space Claim, and what I would do is make a variety of these geometries, or you can just do the one there, export this one and re-import it in again. Now obviously here what we want to do is we want to duplicate this one, and once you duplicate this one you can then replace the geometry from that one with this new one. Or if you wanted to, you can grab your own static structural and drop it onto this one and then do all the settings yourself again in order to analyze and compare. So here, if I click on this one to this one, we'll share, press OK. And if I click on the model, upstream, yes, bring in the new CAD geometry. Give it a few seconds as it brings in the new model. Okay, so you can see it's brought in the new model and there's a few things that are missing. So again here, geometry is structural steel, and as you can see, look at the weight. There's a massive difference. The other one was 1.52 kilograms, now it's only 0.84 kilograms. And then again the mesh, we just need to reselect the whole body, and then right click, generate mesh. May take a little bit more longer this time, but it has meshed. And then obviously fix support, because it's a new CAD model, we just need to reassign all of the edges and paths. Oh, come on, there we go. There we go there. Apply, and then if you press solve, it should just take a few minutes and solve everything that we need. Okay, so you can see here, so you can see now, so 2.58 millimeters is deforming compared to 1.56, so a lot more deformation, and obviously the normal stress taking this value here, so you can see a lot more stress taking place, a lot more deformation for you to compare. And again, the safety factors and the biaxial indicators, you can see here the maximum values, and the fatigue sensitivity as well has changed. So again, it's completely up to you what you do now in order to do your comparison studies. Usually I would have added the topology optimization on this, but for some reason the student version is causing a few issues with a couple of the student licenses. So what I would say is fully analyze the different shapes, specifically the 2D approaches, in order to see what kind of comparison the shapes can have in terms of the structural properties of this beam. Okay, so that's everything for this assignment. So any troubles, do contact me. Thank you.